So last time we looked at IMDb part 1, now it's part 2. Just to recap briefly, I will do that on each and every lecture. So we looked at entity relationship modeling. The entity relationship modeling is a language. It's very important to understand that. So it's the first thing we do as when you want to design a database schema. And we learn about these different symbols like entity types, relationship types. Always say type, yeah, it's not the entity. This is the entity type, relationship types. Then the functionalities, attributes, including key attributes, are underlined, and then inheritance modeled using this R element. Yeah? And we looked at IMDb as our concrete example. Where is it? Here. So that's where we had generalization, and we saw basically that there are these entity types like directors, Regisseure in German, and they are connected to other entity types like movies through relationship types. You cannot directly connect one entity type with another entity type. Yeah, that's basically what we had. And then generalization like an object orientation. So directors are persons, actors are persons and stuff like that, which also means the attributes of directors include all the attributes of the supertype. So directors also has all these attributes, of course. Yeah? So that's the first language we learned, and this language we then translated to a second language called the relational model, using relational schemas, in particular named relational schemas. So that was the second thing we did. I directly jumped to this one. So named relational schema, where we have these definitions of relations that look as follows: attribute name and then the domain name. So for instance, movies become something like this: ID of type int, name of type varchar. Varchar is just a database term for saying that's some string. And for actors, the same thing. There's an ID, first name, and so forth. And this is a key attribute. Key, again, meaning if there's a specific value, say 42 specified, then that uniquely identifies a tuple in that relation. That's very important. There mustn't be two tuples having the same ID, the same key attribute values. That's very important. And then we learned about how to translate the entity relationship model to the relational model. And basically, there are trivial steps and not so trivial steps. So the trivial step is translating an entity type to a relational model. That's just a one-to-one mapping. So basically, whatever you have as your key attributes, yeah, those become the key attributes in the relational model. Whatever you have as non-key attributes, they become the non-key attributes in your relational model. That's it. So that's really trivial. And then more interesting it becomes when you look at the relationship types. Yeah, there you have to introduce these foreign keys or references, as we are calling them, to the corresponding or to the participating entity types. So I jump over that directly. We had that. So we basically use this notation here where we say, okay, this attribute name is of this type. And that is not a domain here. This is saying, no, this is referring to relation, to entity type or relation in this world already, movies, and the attribute ID of movies, which happens to be the key. Yeah? So you make a clear link between those different relations. That's very important. So we link elements from one relation with an element in another relation. Yeah? That's the heart of that. And those links are called foreign keys. Yeah? And we will use this shorthand for the notation. So if you write something like this, relation have, has an attribute name movie underscore ID, which is a foreign key to whatever the key is in relation movies. Yeah? So I'm referencing, so if movies has any attribute, any tuple which has an ID 42, I can simply later on write 42 in this, for this attribute value, and that makes a link between those relations. So I can link through those foreign keys, and that's a very important concept in the relational model. Okay. Yeah, then we looked at the different functionalities, as they are called. So depending on, so if you have something like a 1 to n in this binary relationship type, you don't have to translate the relationship type into a separate relation. You don't have to do that if there's a 1 in a binary relationship. Yeah, then you can do things like explained here. So basically extend the definition of directors to include that foreign key. Yeah, so as you know, the director determines the villa, which means a director may have at most one villa. You can simply add an attribute to the directors relation where you put that foreign key. You don't have to use a separate relation for this. You can do that, but I recommend you don't do that because it blows up the schema unnecessarily. Yeah? So this extra relation is only required if there's an end-to-end relationship or if it's a ternary or more array. Yeah? If it's not a binary relationship type, then you typically have to translate it into a separate relation. Yeah, we looked at the different cases. Yeah, come on, move on. Yeah, one-to-one relationships, the same thing, different options here. Yeah, we didn't look at the notebook. We will do that today a little bit. But then basically what we will be doing today is the question will now be, okay, now we have the data in the relational model. So how do we query that? I mean, at the end of the day, you want to query that. If you look back at IMDb, you have those web pages displaying that data. And how is such a web page generated? Well, on the server side, the server is using what's called a template engine. So there's some sort of a template with placeholders for data, and those data are taken from the database system. Yeah, so the server sends a query to the database system or to whatever system that keeps those relations. So it queries those relations, and the data that's being returned is put into those templates. And at the end of the day, the server serves a standard HTML page. Yeah? So the question is, how do we query those relations? And that's what we will be looking at today. Yeah, so this week it's really how do we query that data. Question number 3, that is the topic of today. And we will use slides and some Jupyter notebooks, way more Jupyter than last time. Those are the learning objectives, again, just for your reference, what we will be learning today. But I will show these things one by one. So what I will be introducing to you today is what's called relational algebra. Again, that's a very old concept. Still, it's used because that's how you should do it. So it's a modular query language for converting one or more input relations into an output relation. Yeah? How that works we will see in a moment. The important thing is when you Google or look up relational algebra, it's a very old concept and it comes in many different variants and flavors. So there's a core set of things that are always the same in different dialects of relational algebra, but there are extensions that exist in one variant and one dialect, but not in the other. It's the same as with natural languages. As soon as a language is created, separate regions of the world will evolve dialects. It's the same with any language in computer science. People will develop dialects. But the core idea is always the same. That's very important. It can be extended very easily. And there are many different implementations of relational algebra. So currently the most well-known is Apache Spark. So if you ever have to handle big data sets, you probably want to look at Apache Spark. Yeah? So if you, so big data sets, I mean like if you go beyond gigabytes and the terabyte range, something like that, you probably don't use a database system for that to start with, but you use something like Spark. And what is Spark? Spark is basically relational algebra plus. It's nothing about that. Yeah? So by the end of today, you will be able to use Spark already for simple use cases to query data and transform data. So that's the cool stuff about that. So it sounds like a really dry theoretical topic, but it's exactly what you will be writing down if you're using Spark to handle big data sets. It also has many other important use cases. It's in particular, it's used internally by systems for what we call query optimization. We will be looking at that in this lecture for, I don't know, in June or something like that. I will give you some ideas on how that works and why relational algebra is important in that space. And it's used directly to write data programs, data flow programs. like in Spark. So it's really something that can be used in a productive environment. So what is this, a relational algebra? So basically, it's just a couple of operator definitions. So what is an operator? An operator is a function that takes as its input one or two input relations. Yeah, so that's a parameter, one or two input relations, and outputs a relation. That's it. So a function operating on relations. Yeah? Maybe one or two input relations, but the output will always be one relation. Yeah? That's this thing here. So this expression, this power set, designates the set of all possible relations. For historical reasons, only unary and binary operators are allowed. Just to mention that, it's really an unnecessary restriction. However, we will stick to that in this lecture to make your life easier. And you will also see that in, if you look it up in textbooks, people always talk about unary and binary, but not ternary or something operators, which actually would make sense in certain situations. Yeah? But for the moment, or for this lecture, let's really stick to unary and binary. And one confusion I want to mention, because it happens very frequently, is so if you write down these operators, so it will look like a function tree. Yeah? So one operator nested, one inside another, and stuff like that. And that looks like a sequence of operations, so an order. Yeah? You first run this operator, then the next operator, then the next operator. So it looks like a procedural program. That's a misunderstanding. Relational algebra actually can be read in a declarative way. Yeah, so a relational algebra expression just specifies what you want to compute, but not how it's going to be computed. Yeah, the same actually holds for these implementations. So if you want to play with systems like Spark and you write down these relational algebra expressions, it looks like it first does this, then it does that, then it does this. No, the system can decide, no, I do it in another order, in another sequence. As long as the semantics of the expression are preserved, that's totally fine. Yeah? So even though you specify it in that order, the system may decide to execute it in a different order. Same actually happens for programming languages. You specify it like that, the compiler understands, oh no, I could execute it in a different way, the semantics are preserved, blah, blah, blah. You don't even notice this stuff. Yeah? And it's the same here. Yeah, and the significance for data analysis and processing is like the periodic table of elements in chemistry. It's really, it's so fundamental. It's like you see it everywhere. Yeah? That's why I try to put it in, not with the number of neutrons and what is it, electrons and stuff like that, but that's kind of that's how this periodic table of relational algebra operators looks like. There are more, don't worry, we're not going to look at all of those. So there's basically a core class, or basic operators. Yeah? Those are those operators here. It's hard to avoid those operators. You need those operators. And then there's a large set of derived operators. Derived meaning you don't really need that stuff. That's kind of syntactic sugar. All of these operators can be, question? All of these operators can be expressed using only these operators. Yeah? You wouldn't actually need those, but these operators here, those derived operators, make your life easier when writing down these expressions. Yeah, then there are a couple of very important extensions. One is grouping or group by. You see that frequently in query expressions, and that is strongly related to an operator that's called co-grouping. That's not so common, but we will use that in that lecture because it makes a nice link between what's called a join operator and a group by operator. Co-grouping is just a generalization, and you will see how things come together once you understand co-grouping. Yeah? But we will get there, don't worry. So one comment that you often see in literature and people believing that they understand databases, but then you find out they don't. And it's very important to understand that. So I talked about domains before when defining the relational model and when saying, okay, we have an entity relationship model, we don't care about domains in the entity relationship model. And then all of a sudden, domains appeared in the relational model. We said attribute name, colon, integer or something like that. So integer was the domain being used. And originally, when the relational model was created, invented, those domains were forced to be atomic values. Yeah, that's very important. Yeah, and many people still believe it has to be like that. It doesn't. Yeah, so those values had to be structured, not further divisible, whatever. Yeah, so you had types like integer, float, string, and stuff like that. And that leads to a database theory called normal forms or normalization. Did any of you had that in school? Normal forms? Yeah, okay. Up to which? Third normal form or more? Fourth, fifth, boys caught? Fifth, okay, cool, okay. And yeah, so that's again, so I said in another lecture, so there's actually a Slack group for the database professors in Germany. Yeah, we just discussed that. So do you teach normal forms, yes or no? I'm in the team, no. But there's a team, yes. Yeah? And the point of normal forms is, if you do your entity relationship modeling right and do the translation right, all your relations will be in what's called third normal form already, naturally. Yeah, so you don't have to worry about that. So normal forms are about redundancy in your relations, and yeah, I don't have to go into details here. The point is, normal forms are important if you have a schema that's messed up. If you see, oh, there's a lot of redundant information, or the name of that student is stored 10 times, yeah, that's pretty weird, I should only store it once. Then you want to look at these kind of things as normal forms. So basically when reverse engineering a database schema, or when looking at a messed up schema, these things happen in practice more often than you wish they would happen, they should happen. Yeah, then normal forms are interesting, and then I invite you to look at that. Yeah? We won't do that. But this theory was created based on this assumption, on atomic values. And in modern SQL, where modern means the standard that's more than 20 years old, so SQL 99, you don't have that restriction anymore. We actually will see in this lecture that we can have domains that are relations. Yeah, so you have a tuple, yeah, and maybe one attribute is of type int, the other attribute is of type relation. Yeah, so the tuple contains a nested relation. That's totally fine and is supported by many modern database systems. Yeah? And just for you to keep that in mind, domain can actually be anything, yeah? Not just integers, strings, whatever. Okay, so that's a periodic table of relational algebra operators. Let's look at some of those operators. A note on the notation used in this German database book by Alfons Kemper. So just to avoid that confusion, since it's usually clear from the context whether R denotes the relation, including the instance and the schema definition, or just the instance, I will often write just R instead of these curly bracket R in the following. Yeah? So it should be clear from the context what is meant, so I want to avoid these writing down these complex expressions every time I do an example. Okay, yeah, how do we do that? In which order? Maybe let's start with some slides here. So here this slide is just for completeness. We will use these expressions in the following. So we need to be able to reason about those relational schemas. Yeah, we need those, as schemas are sequences and not sets. We did this slide. So basically, we need to decide things like, now you have a schema definition. Is attribute A contained in that schema, yes or no? Yeah? Or what does a subschema even mean? So subschema means, so all the attributes contained in R are also contained in S. Yeah? So S is typically a superset of R, stuff like that. What does intersection of these two schemas mean? What does union of these two schemas mean? And just for completeness. Yeah? But maybe I will explain these again once we use these expressions. Okay, let's jump right into the first example. Again, I won't go through each and every slide, so the slide set also contains some more theoretical definitions for you to read back home. So I will focus on the practical examples and explain the concepts using those practical examples. So selection, or sigma, that's the first and actually the most important operator. That is selecting a subset of the tuples. Maybe let's start with an example and then go to the definition. So assume you have these two relations R1 and R2. R1 has these two tuples, R2 has these three tuples. So we really have a schema only consisting of one attribute, only one attribute in the schema. That's fair. And then what we can define is a so-called predicate or selection predicate. That's just a condition that must be phrased against the schema of the input. Yeah? So here in this condition you see I'm referring to an attribute called ID. Yeah? So if that ID is contained in this schema, it's okay, that's fine. So I mustn't write A or B. Yeah? If I wrote A smaller equal 2, yeah, something like that, and I wrote A smaller equal 2, that wouldn't work because A is not defined here in the schema. So what this does is, it returns the result set. Yeah, so you write it like that. So you have an input relation R, you have the selection operator, it has a parameter that is this P, and that's a predicate that is phrased against that input relation R, and the set returned is this one. So all the tuples from R in R that qualify, that fulfill the predicate. Yeah? That's where the predicate returns true. Yeah? So all the tuples where the ID smaller equal 2 are being returned in this case. So if you run the selection, if you run this predicate against relation 1, you get this result set. If you run it against relation 2, you get this result set. Yeah? And these 3 and 4 are not returned. So it's a standard operator you will use to filter data, to restrict it to certain expressions. So in the IMDb example, so if you have those 3 directors, you can say something like, oh yeah, give me all the directors where the ID is greater 45,000. Yeah, and that would only be Quentin Tarantino in this case. Yeah, well, I mean, this selection, do you think that makes any sense? Do you believe you would see that in a real system? You're shaking your head. Why not?
I don't think it makes any sense because the ID is just supposed to be an identification and is not sorted in any way.
Yeah. Actually, it's just a symbol, a categorical symbol. It is a sort order on IDs should not make any sense. If you see a query like that, alarm bells should ring. Yeah, equality makes a lot of sense. So you look for a specific symbol, but a range of symbols, I would take a look at what's going on there. Yeah? I mean, here wouldn't make it. I mean, you would typically have a query like ID equals 78,273. Yeah, that's what you would expect. So here another query against strings. So for the first name is Stanley, and then you get Stanley Kubrick, and so forth. Yeah? So that's a selection operator. Here again have more examples for those predicates. So predicate is defined on the schema of the input relation R and maps to bool, so only returns true or false. Here's a couple of more examples. So here you have a schema with ID, A and B, and then you can reason about what is valid and what is not. Yeah? So for instance, this is not allowed because C is not part of that schema. Yeah? So it's not well defined. That doesn't work. Okay, so with that we get to the second operator. That's the projection. Projection operator also similar to what's used in mathematics. Again, let's start with examples. So we have a schema with 2 attributes. That's our data. And what the projection needs to define is a subschema. A subschema meaning any subset of those attributes of R. So I'm saying, okay, this R prime is a subset of R. And now I only use this A attribute. Yeah? So that's contained in R, everything is fine. And what the projection operator does is it takes that input R and returns tuples that are only mapped to this schema. So it leaves some attributes away. So if previously there was a 1.3 referring to A and B, now we only have a 1 which refers to A because that's what we map to. Just projecting the tuples to a different schema. And the same happens for 3, yeah, and the same happens for 4. And here the 2 is colored in red and green because, yeah, if you project to attribute A, basically those two tuples, 2.4 and 2.7, are folded into one tuple as the relation is a set. Yeah, that's not a multiset. We don't preserve all of these 2s. There can only be one tuple with the same attribute values, and that is why it has 2 colors. Yeah, the same happens here. Assume the subschema is attribute B. Then the same happens for the 3, because this blue 3 and this kind of dark red 3, they will be folded into this single 3. Yeah? And that's important for these projection operators, because you will see that the number of tuples returned by a projection can be smaller or equal the number of tuples in the input. Yeah? So, and to facilitate the discussion, I want to introduce something what we call cardinality. So what's the cardinality of a relation? So if R is a relation, then we have the cardinality is a function like that, mapping to an integer, a positive integer, including 0. That's called the cardinality of R. It returns the number of tuples contained in R. So basically, it just counts the number of tuples in a specific relation. Yeah? And then for the projection, it trivially holds that whatever you project to, whatever the schema is, it can only be as big as the input schema or smaller. That's that actually holds. And you see, here's again the explanation on the slides. On the slide, an example for the IMDb example is something like that. So if you run a projection on this genre attribute on relation movie genre, you get 17 tuples. But if you do it on the input, if you just count the number of tuples in movies genres, you get 102. Yeah? So that's basically the effect of a projection operator. What else do I need to say here? No, I think that's all I need to say. Should we do the notebooks? I'll walk through a couple of more operators, and then we switch to the notebooks. Yeah? So these operators are basically set operators. Yeah? Maybe you learned about them already in some math class. I think even in schools it's taught. It's very similar. So the difference being, so typically when you learn about set-based operations like union and intersect, you only do it on integers. Yeah? You have a bunch of integers, another bunch of integers, you union, intersect, make the difference or whatever. Yeah? The only difference here being is the relational model, so we have tuples. Yeah? That's the only difference to the standard set theory. So union operator combines the tuples from two relations, two input relations, R1 and R2, so it's a binary operator. The following precondition must hold. So this is now an expression on the schema, meaning R1 has the same schema as R2. So all the attribute names in R1 are the same attribute names as in R2, and all the domains are the same in R1 as they are in R2. That's what I showed on this slide with these schema expressions. Yeah, and if that is the case, if the schemas are the same, then the result of the union can be written down like that. So it's basically all tuples from both inputs are unioned into a new relation R prime. Here's an example. Again, R1, R2 schemas are the same. That's fine. If you do the union, again, you get this result. Again, the 2 is folded into one tuple. Yeah? So, and that is why the number of tuples in R is limited. Yeah? So in theory, the maximum you can get is number of tuples in R1 plus number of tuples in R2. But due to duplicates again, this can be smaller. Yeah? Because here in this example, these two 2's are folded into this one 2. Yeah? Right. Yeah, and here's a similar example for IMDb. So both new as well as good films combined in a single relation. So new films is a selection where the year is greater, strictly greater 2000. Union, all the movies where the rank, that's a quality attribute in IMDb, is greater equal 7.5, and you put them for whatever reason in the same relation. Yeah? That's one use of the union operator. Yeah, then there are all the other set operators you would expect. So difference, that's also called minus or except. So similar conditions as for union only works if the schemas are the same, are identical. And here's an example. So basically, whatever tuples you have here, so if the tuple occurs in both of those, you don't return them. Yeah? So basically R1 minus R2 is 1. Why? Because this 2 is removed from the result. And if you do it the other way around, R2 minus R1, again, the 2 is removed from this R2 result. So in other words, you can only get a subset. This expression will return a subset of R1. This expression will return a subset of R2. And then you can make the reasoning about the cardinalities as before. So that's a difference operator. I'll walk through these more quickly. Should I do? I think we do the base operators and then I do the notebook. So I have two notebooks, and again, they are on our GitHub page. So there's one for the relational model and one for relational algebra. And on the relational model notebooks, there's not too much to learn. It just shows you how to import this stuff here in this cell, and then basically how do you define a relation. Yes, you can. That's the relation name, and then you can define the schema here of that relation. So with two attributes, ID and name, and then you basically add tuples. Yeah, and then you get this as a result. Okay. We also have a sample data set we're using on the slides. You can directly use in those notebooks. So there's a couple of CSV, comma-separated value files that are read in this notebook. And we do a little trick here with this globals statement where we define variables that have the same name as a relation. So what that basically does is, now you can directly write actors in your notebook, and that is the relation actors being returned. That's quite handy actually for working with the data. And just write the relation name and it makes life easier. Yeah, we have different output formats that you can use on those relations. And different display options. You can limit the number of rows at this max row limits. Sometimes that's handy. Also for your exercises, I recommend you use this stuff. You can output it in a more like in a set format that's more akin to what I'm using on the slides, more the Kemper notation. Or if you want, you can write it as LaTeX and put that into your LaTeX document, and that should compile directly, or run it in those sets, whatever. That's all you have to know. So it's all these relations in your notebook. And we use these relations, of course, for our relational algebra expressions, and that's the second notebook. So here I have to import a couple of things. So maybe it's worth mentioning that, just briefly, I don't have to. So that there were some people that had problem with a virtual machine. I just wanted to mention that briefly. So basically, if you go to our CMS, now we have this manual installation explanation. Yeah? So if you want to install it on your host machine rather than using Vagrant and VirtualBox, you can do that. And basically, what you do is you create what's called a virtual environment, and then you have a requirements file that you install, and then you should be good to go. That's, for instance, how I use it. Yeah? I think there are 3 different virtual environments, at least for Python, that you can use. We use the built-in one. So that's how you could do that. And most of the notebooks used in this lecture will work with that. Yeah? Roughly until end of June, the notebooks. There's some that don't, because for some you need certain systems to be installed. Those systems are installed in the virtual machine, but not if you just do this manual installation. But don't worry, for the exercises it will work. Yeah? So if you want, you can also use this manual installation I'm using this here for the lecture myself as well. Okay, so back to that one. So now you can load data sets, same as in the other notebook. So I'm loading this IMDb data into my relations. Yeah. And then what I do here is a little trick. I wrap those relations into what I call a leaf relation. So oh, there's some doors open, huh? Okay. So I wrap them in a leaf relation, so that this leaf relation basically behaves like an operator. Okay, let's do that. And then I call evaluate, and then I basically print the set again. So evaluate returns the relation being computed by an operator. I can print it in LaTeX again, or I can print it as a graph. That will be important in the following, because all these, as I said before, a relational algebra expression can be displayed as a tree. Yeah, and I will also display them as a tree in the following. Always read those trees bottom up, from bottom to the top. It's just a visual representation of these operators or relational algebra expressions. Yeah, and then you can do stuff like that. Yeah? You say, okay, my input relation is movies, and I want to use this condition here and use a selection. Yeah? So basically, that is the Greek letter representation, plus there's some underscore thing. So that is something that we will touch a bit later on in the lecture. However, we already have to write it here, because if I only wrote the Greek letter, if I only wrote sigma, unfortunately, Greek doesn't understand relational algebra. So Greek is not an algorithm, let's phrase it like that. I have to specify an algorithm. How do I want to evaluate the selection operator? And the algorithm is what comes after this underscore. Yeah, so underscore scan-based means this operator will loop over each and every tuple in the movies relation in the input, and for each tuple it will check whether that predicate holds or not. Yes, if it holds for predicate, it's part of the output. If it doesn't hold, it's not part of the output. So it's a scan-based approach. Yeah, of course, there are much better ones. We will look into that later on. But this is basically just saying, hey, that's the algorithm I'm using. And we will see later that for any given Greek letter or for any given operator, there will be multiple algorithms. Yeah? For the moment, you can simply ignore the stuff under the underscore. That's just in a notebook, I have to say it. I have to specify how do you compute the stuff. Yeah, and then you return here the result set, and can also grab the name of the result set and display it as a graph. Yeah? And that's the kind of graph expression we are now building stepwise, saying, okay, there's a movies relation. The data is flowing from bottom to top. It's flowing into this operator, which is a selection on this condition. Okay? Color doesn't mean anything. It's just a bubble. Yeah? So it's just a bunch of bubbles connected in a tree. For the moment, the tree is acyclic. You can also tree is acyclic definition. Yeah, so it can be an acyclic graph as well, but for the moment we only have the tree, a special case if you want. Yeah, then you have projections and all the other operators I showed you on the slides already. So here that's a projecting to those two attributes. Yeah, and if I run through that, I get a graph like that. So movies is filtered, and then whatever the result is, it's projected to those attributes. Yeah. Union, that's another operator we had. We can specify it using the same signature. So again, input relation, condition, and that's the selection we had from above. But then now you do a union on two inputs, the good movies and the new movies. The example is also on the slide. Yeah, and then you basically get those results. And then, now it's starting to become a tree. So as we have two inputs, one from the left and one from the right. And here you could already argue, because movies is used twice in the query. Yeah? So that's one way of visualizing it like this, like repeating this bubble with the movies, but alternatively you could also don't show it here, but just make a second arrow from movies to this operator, of course, and then it would be a directed acyclic graph. Yeah? There are many ways of visualizing these things. Yeah, that's just one way. Yeah, and so forth and so forth. So I invite you to go through that. So it's really very close to what I'm showing on the slides. But one thing I wanted to mention, because I ran into that yesterday and I found it so cool. As you know, I'm a big fan of these assisting tools, these AI tools. And yeah, now they integrated ChatGPT into Jupyter notebooks. Yeah? And you see these symbols here. Yeah? And those are going to ChatGPT. And basically what that means is you can do many different things. So one is explain the stuff. So basically just click here, hit explain, and then it will be complaining, hey, add my documentation. Yeah, so it explains each and every import statements. So in the previous iteration where I did that, it really complained, hey, you should add more documentation. It's really good style. In other words, it's bad style what you were doing, Jens, right? And these kind of things. It's sometimes really, come on, shut up, man, right? I mean, I do whatever I want. Yeah, but that's really cool. Yes? And so the interesting thing, it's not only for understanding code from other people or understanding the code you wrote 1 week ago and have no clue what it's doing, but it's really also able to propose things. They're like these other AI tools. I didn't try that out yet. So if anything is broken, yeah, if you want to write anything, I can give it a try. I don't know whether it's as good as a PyCharm. Yeah, maybe using an input array, write a function that quick sorts the data using input array of tuples, write a function that quick sorts the data on the second attribute in descending order. Let's see what happens. I think there's some completion thing. I think it's this one, right? So let's see. Yeah. I mean, it's a little bit depressing as well, right? Yeah, it looks right. Yeah, there's recursion, middle append, quicksort descending left, quicksort descending right, middle is a pivot, looks good. Oh, there's an example. Yeah. Come on. Here, there's a copy function, of course. Yeah, okay. So let's see. Banana, peach, yeah, it's correct. It's sorted on the second attribute. Where's the second attribute? Data len. No, takes the pivot is taking the not 0 but 1. Yeah, yeah. I mean, it would be stupid not to use this stuff. Sorry, yeah? You must use this stuff. That's the reality. It's a productive. I mean, quicksort's probably not what you want to code from yourself. You will call a library call on sort, right? I mean, sure. Yeah, but for any stuff you create anew, it's really cool. Yeah? So these tools are here to stay, and it's a big revolution happening. Yeah? So again, if you integrate that, I actually pasted a link here in, where is it? In materials. Yeah, here. So that's a video where I bumped into that stuff that's explaining it. That's 6 minutes or something like that. All you need to do, you have to have an OpenAI account. Yeah, okay, that's the downside. And then there you create an API key, but you don't have to pay for the stuff. So it's really for free, as long as you don't use the speech feature. Yeah, so there's actually a feature where you just, something like that. I'm not going to try it. I don't want to pay anything for that. Yeah, but you ask a question. Hey, could you solve my assignment sheet for the database class of Professor Dittrich? And then see how we grade your result, right? Should I just play it again with that ChatGPT in Jupyter Notebook and actually ask it to write an algorithm that we will be looking at later on the slides, and the algorithm is structurally correct, the ideas are correct, it just totally messed up how it instantiates relations, so it didn't understand how I do that, but other than, I would have to fix that now. But other than that, it's correct. This is the API, it called doesn't exist like that, it was just using something, assuming something that makes semantically sense. It used insert rather than what we use add tuple for other reason, and some of the brackets don't work. But structurally, the algorithm is correct. First shot is correct, so that's actually super impressive. Anyway, so let's look at some more involved operators, more database-style operators. And the first, like more database-style operators, actually the cross-product, also called Cartesian product or cross-join. And again, start with the example. So again, we have two input relations, the one used above again, and the cross product basically combines the tuples from the two relations. So for each, so this tuple from relation 1 will be combined with all of those tuples from relation 2. This tuple from relation 1 will also be combined with all of those tuples from relation 2. Yeah? So basically, if you have n tuples in R1 and m tuples in R2, the result set contains n times m tuples. And that's what you see here. Yeah? So you have, that is a result of the cross product, so a combination of all these tuples from the two relations. The cardinalities, so R1 contains 2 tuples, R2 contains 3, which means that the cross product contains 2 times 3 equals 6 tuples. So basically, what we do is we do this concatenation of tuples from the both input relations. Yeah, and important, of course, is that we create a concatenated schema. So that's again what I had on this slide where I introduced these. Yeah, we can go back to that. Now it's time to go back to that. So this here where I define the concatenation of schemas. Yeah. So that is allowed if there is no common attribute among those two input schemas. Yeah? If there is an intersection that's actually defined there, then this concatenation is not defined. But if these two schemas are disjoint, then you concatenate the schemas into a new schema, yeah? And that's basically the union of the attributes contained in the both input schemas. And that's what we're doing here. So basically, for this cross product, where's the cross product? Here's the cross product. You see there's no intersection in the schema. The one attribute is named A, the other is named B. So the new schema that's being created is A, the colon int, comma B, colon int. Yeah? So with two attributes. And that's the cross product. Okay. And I think we'll skip over that. Those are all derived operators. So let's look at the more database stuff. This is the most important operator you will ever see in this lecture, other than grouping. Yeah, but that is an operator that is a special case of the cross product, if you wish. So what does this do? So this is syntactic sugar, meaning I can express this operator through the base operators. Yeah, so how do I express it? I express it as follows. I say this operator, which is read as a theta join of R1 and R2, it returns the cross product of R1 cross R2 filtered by, so this is a sigma, the selection operator, this predicate. So what I define here is a predicate, I mean, if you think along the lines of this expression programmatically, so basically you build this huge result set, yeah, R1 cross R2, so basically it's a squarish size of that set. And then for each tuple, again, you run the selection and check each tuple in this input whether it qualifies this predicate. That's what we're doing here. So basically, an example explains more than these definitions. So somewhat changed example here. So we have the blue tuples and we have the red tuples. And now we run this operator. We have this schema concatenation here. So this new schema being built. And if I have an expression like this, it returns those results. Why those results? Because I have this theta predicate saying, yeah, the B attribute, B is contained in relation R, must be equal to the C attribute of relation S. Yeah, so that's the B attribute, that's the C attribute. I have it signaled through double underline. Yeah, so only those tuples here are returned where the B attribute value is the same, is equal to the C attribute value. Huh? So that holds for all of these results. So in other words, what I'm returning is a subset of the cross product where this condition holds. And the same here in the second example. Here I make a condition on A equals D, so that must be equal to this one for the tuples in the result set. So why does anyone have an idea, without looking at the slides, the other slides, why that operator could be important for us in the relational world? Why is that the most important operator in the following? Yeah?
Maybe if you're doing something with two entity types that share attributes, for example, then you can basically see to it that they match up properly.
Yeah, almost correct. You don't have to share attributes. You just phrase a condition where part of the condition goes to the left input and part of the condition goes to the right input. And if you think about relational schema definitions, did we have something like that? Where there was something in that schema referring something, yeah?
You can take the foreign keys and then get other entity.
Yes. The foreign key definition and the relational schema. So the idea of having foreign keys, the idea of having separate relations for directors and the movies they make is to avoid redundancies. I don't want to have one large tuple where for every movie of Quentin Tarantino, there's a complete record for Quentin Tarantino. I don't want to have Quentin Tarantino Inglourious Bastards, Quentin Tarantino Kill Bill 1, no, I don't want to have that. I only want to record Quentin Tarantino once, yeah, and all the movies he made once, and then have links between those different tuples. So don't have redundancies. That's very important here. So we basically split those long records. If we had those long records into those entity types, into relations where the redundancy is gone. Yeah? But now if you want to query that data, we are reconstructing the data along the foreign key conditions. And the foreign key condition is exactly what we see here. So that's the joint predicate, the theta joint predicate. So basically those conditions will typically be phrased, this one actually, will typically be phrased against foreign key conditions you find in the schema. Yeah? You can also use other attributes. You're fine to do that, but typically you will be messing up your result. Yeah? So if you look at the IMDb schema here, that's an example. Yeah? That's a foreign key condition. So ID is the key in the directors relation, and director ID is a foreign key in the movies directors relation. Yeah? And now we are reconstructing tuples along that foreign key condition into one big relation. Yeah? So we're going back again from two relations into one relation, and you will see here, hey, oh, I have a lot of redundancy here. Yeah? So you wouldn't want to store it like that. You don't want to store the directors, here's Tarantino multiple times. Yeah? You don't want to store the name multiple times, but in the result set, you will see those redundancies. Yeah? So that's a theta join, and it's very important when you want to relate data from one relation with data from another relation, because you will always write down those foreign key conditions again. Okay. Right, yeah, okay. Yeah, and then this theta join is basically the most generic join you can write. Yeah, you can basically write any predicate here. For practical reasons, sometimes we restrict this type of predicate, yeah, to a specific operation. Of course, if you use if you join along foreign key conditions, you only want to have equality. I mentioned it before, this ID with a smaller equal doesn't make any sense. Yeah? So you want to have equality. I want to have the tuples with 42 from this relation and with 42 from the other relation. Equality is fine. And that's a special case of a theta join that's called an Equi Join. And maybe I directly jump to this more formal slide, is better here. So basically what you can do to specify such a join, something like that. You just write in the join, that's the important thing here, the attributes from the left input you want to use for the join predicate, followed by a semicolon, and then the attributes from the right input that you want to use for the theta condition. And this is automatically translated to this condition here. Yeah, so A1 must be equal B1 and B2 equal B2 up to AN equal BN. And that is again the theta join predicate. Yeah? So sometimes you just specify it like that because for all we will be doing when joining data, it's only equality in this lecture. There are cases for joins where these things make sense, having a smaller or greater, something like that. In particular, when you look at spatial data or temporal data, yeah, then there are cases where you will do these things, but for a standard relational schema as used in this lecture, it will always be an equality condition in those joins. Okay, and maybe let's switch to the notebook again. What do we have? Here's a Cartesian product, cross product. Let me just show it briefly. Here see this result. You have 3 tuples here. And 7 tuples in the other relation, so 3 times 7, no, not 3 times 7, 5 times 7, skipping 25 or 7 tuples, director genres, whatever, what do I even compute here? Directors times director genres. It's not divided, there must be a bug, I don't know, what else? 35 is not divisible by 3, right? I don't know, there's a bug. I need to double check that. Yeah, but basically, if you have n tuples in one input and m tuple in the other input, that's what you should get. I mean, let's debug into that a little bit. Director genres, Cartesian product nested loops, print Cartesian product, directors evaluate. Let's do director genres evaluate. No, not this one. What's wrong here? Oops. Director genres. So that's only director genres. Oh, sorry, of course. Director genres is 35 tuples, yeah, and then the result set. Okay. And then it's 35 times 3, of course. Yeah, the cross product is 35 from director genres and 3 times 3 from directors. So the product is the result set. And of course, I mean, there are reasons why you would use Cartesian products, but typically you don't. Yeah? Just simply because the result set explodes so much, it doesn't make any sense. Yeah? So for special cases, analytical queries, sometimes you use it, but actually it's just something you want to define for completeness, but not really use in practice. Okay, so let's look at the theta join. So here's an example. Again, these 2 inputs. Here's our join predicate. Yeah? And then basically what this returns is a graph like that. So this bow tie is a symbol for the join being used, and with these 2 inputs. Yeah? And of course, you can then add more joins to the result of that join operator. Yeah? So if you join not only 2 tables, but 3, 4, 5, whatever, you can add more join operators, as we have that restriction that the join operator is binary. You can only at a time add 1 relation to the result. Yeah? Okay, yeah, with that, let's move to grouping. That's an important extension, and maybe that's the hardest to understand. So from the experience from previous lectures, we see that triggers many questions, and that's why we have many slides on that operator on the slide set. The confusion here is about this operator is, in particular, it's actually doing 3 things at the time. So one is horizontal partitioning, the second is aggregation, and then it's doing a projection. So how do we start that? Different ways of explaining that. let me maybe start with that slide. No? Let me start with that. So group by is a term also used in systems. Later on, when we talk about SQL, you will see that that's a term being used. And that's a bit misleading because you have these three operations. And let's start with grouping. Yeah? So what does grouping mean? So group by is a unary operator. So one input relation. And the first thing it does on the input relation is it horizontally partitions the input data. So what is horizontally partitioning? What does that mean? I have an extra slide for that, of course. Horizontally partitioning means that depending on a specific value, you split your data into subsets. Yeah? And so if you have a relation like this with 4 input tuples, if I decide to partition that into subsets, any of those 2 here is a horizontal partitioning. Yeah? So the only thing that I'm doing is I'm splitting this input relation R into subrelations R1 and R2, and the condition that has to hold is I can reconstruct R at any time just by doing a union of R1 and R2. Yeah, so I'm just redistributing the tuples from R into subrelations, as I'm calling it, and that's called a horizontal partitioning. Why horizontal partitioning? Because a relation is typically visualized in a table style. Yeah, and if you partition it with scissors like that, yeah, you do a horizontal cut of that table into horizontal slices, horizontal partitions, and that's what I'm doing. Yeah? If you have this notion of a set, horizontal doesn't mean anything, but if you visualize it as a table, that's why we use this name. Yeah? And then the important thing is disjoint horizontal partitioning. So disjoint meaning there is no duplicates in those partitions. Yeah? So so in this example, yeah, this example shows us pretty well. Yeah, so this is a valid horizontal partitioning. However, one of the tuples, this 2.a, is represented twice. Yeah? It's contained in both of these subpartitions. That's not what I want to have. In the following, I want to have a disjoint horizontal partitioning. That's typically what's used in group by. Yeah, and if you have these partitionings, you can think about, okay, how do I partition anyway? On which condition do I partition my input data? And this is done through a partitioning function. So a partitioning function maps from the input domain, so that relation, to a target domain, can actually be any target domain. Again, an example, assume we have a function like this, yeah, returning the value of attribute A modulo 2. So basically returning whether A is even or odd, right? Yeah, so you can only return 0 or 1. So for these different tuples, you get these results. Based on that, you can induce a partitioning. Yeah, so you can say, okay, now I put all of these zeros into 1 and all of these 1s into one subrelation. Yeah? The same you can do with any other partitioning function. If you say you define a partitioning function on attribute B, yeah, just returning the value of B, in this example, you only get these results for these 4 input tuples. So just by defining such a partitioning function, you can automatically create a horizontal partitioning. Yeah? And that looks as follows. That's called an induced horizontal partitioning. So if you use this partitioning function here with those calls to that partitioning function, the induced horizontal partitioning is this. This partition R0 contains those tuples that return 0 when called with a partitioning function. Yeah, so as we only have 2 return values in this particular example, there are only 2 subpartitions. Yeah? So this is everyone returning 0, everyone returning 1. Yeah, I do the similar thing here on the right side. Oops, on the right side, where I say that's my partitioning function. Of course, I mean here in this example, I only have 3 different values being returned. Could be many more, depending. So that's just what's the domain here? It's character, so it can be a number of characters in the alphabet. Here it's only 3, so that is the result. That is the induced horizontal partitioning. Yeah, so I define a partitioning function, and that implies that I get some subset of that data. Okay, so with that, we go back to this grouping definition. So that is what's happening here. It's horizontally partitioned, and let's assume for the moment it's a disjoint horizontal partitioning. So the group by operator takes the input and depending on the condition, yeah, so what is the partitioning function is the obvious question here. It creates a horizontal partitioning. Yeah, how the partitioning function looks like we will see in the moment. Yeah, but it's the only high-level idea that happens at this point in time. Split the input relation into subrelations that form a disjoint horizontal partitioning. Step 1. Step 2 is aggregation. For each group, or horizontal partition as I call it, created in step 1, we run that group through a set of aggregation functions. Yeah? So for each group, each of these functions is applied independently. So what is an aggregation function? It's a function that, maybe now I can show this slide, that takes an input relation, typically, sometimes it also specifies a specific attribute to look at, and returns one tuple. Yeah? The easiest example for an aggregation function is count star. Yeah? If you input a relation into count star, you're back to the cardinality. Yeah? So that's basically the number of tuples contained in that horizontal partition is returned by count star. Yeah? It must be at least 1. Otherwise, there wouldn't be any horizontal partition. Yeah? So you don't create horizontal partitions without any tuples. Yeah? So it must be at least 1. Yeah? Or something like that. You could say, okay, I have my horizontal partition with, I don't know, 50 tuples, and now please look at attribute A in those tuples and return the maximum value. Yeah? So again, of course, attribute A should be defined against the schema of the input relation. Yeah? So you can use as many of those aggregation functions as you want in a single statement. Yeah? So build those partitions. For each partition, call the aggregation functions. And then third, project the result of the aggregation plus other attributes to the output. And I think now it's time to look at some examples. For instance, yeah, so here again, a toy example with our 5 tuples we had before. And now the question is, what is a partitioning function? So in the group by operator in relational algebra, but also later on in SQL, there is no arbitrary partitioning function. Again, it's equality in the cases we use in this lecture. So I write the operator as follows. Yeah, that's the notation you will see many times. Oops. Yeah, so that's our Greek letter again. And then there are 2 parts here that you see as a parameter specified to the operator, to the group by operator. The first is specifying, okay, what is the condition to use for horizontal partitioning? Yeah, and this A is saying, I want to have an equality condition on the attributes, meaning all tuples where A equals 42 go to one partition. Other tuples where A equals 45 go to another partition. Yeah? So, and so forth and so forth. That means within a horizontal partition, the attribute value A of all tuples is equal. Yeah? So you build those horizontal partitions based on equality again. Equality is super important in the relational database domain. So that's exactly what we do in this example. So basically, we partition first. We build the following partitions. This is one partition. This is one partition. This is one partition, and this is one partition. Okay? Then comes the second step. We run the count star aggregation function. Yeah, for this partition, it's 1. For this partition, it's 2. For this partition, it's 1. And for this partition, it's 1 again. Okay? Now comes the projection. the projection is reusing your partitioning condition. Don't blame me for that. That's how dudes back in the 80s defined that. Yeah? There are better ways of doing that, yeah? But that's how it works. So we used this already to define how we partition the input relation. Now we also specify how we output this stuff. Yeah? So this is now read as a projection. We are in step 3. Saying, okay, I want to output a schema. So the output schema contains 2 attributes. The first is the attribute value of A. The second is this count star result. You just computed in step 2 as the aggregation. So meaning the horizontal partition here has a value of A1, so that's this one. And then there should be a count, that's this black one being computed here. Yeah? This partition has this A value 2, that's this 2-colored 2 again, and the count, of course, is this black 2, yeah, and so forth. Yeah? So this is dark red 3 with a count of 1, and this is brownish 4, that's this one, with a count of 1. So that is the result when you group by A, comma, count star. Yeah? Now I do it in the second example, I do it on B. Yeah? Same thing. So what are the horizontal partitions based on B? Well, if you look at B, there's a 3 here and there's a 3 there, so that's definitely that's one horizontal partition. Then that's one, and that is one, just based on that attribute B. Yeah? So again, the same thing. So I have thank God it's only 2 colors, not 3. Then I had to put a heck more. I don't know how to do 3 colors in a number in LaTeX. Yeah. So this has 2 colors, and again, this count is 2. Yeah. This group had 1 element. That group had 1 element. That group had 1 element. So that is the result. Okay. And now, if you switch to examples from IMDb, you see, yeah, that makes a lot of sense. Yeah? So for instance, you can now write it like that. So for instance, count the number of women and men among the actors would be something like that. So you just say gender, comma, count star. And here we only have 2 possible values. Of course, in a modern database would be more possible values. Yeah, so we have a count star giving us an aggregate. Yeah, so a summary of the data, yeah, statistical information about the data. Or here, that's a query that's super useful. Okay, so for all of these actors, for all of these directors, I want to know how many movies are present in my database. Yeah, so Quentin Tarantino did 10, Stanley Kubrick 16, and so forth and so forth. So count the number of movies done by those actors. And if you don't specify a condition here, yeah, if you don't say, I want to build groups, I want to build horizontal partitions based on that condition, you could also do that. You just write an aggregation function here, count star, and then it will simply count the number of actors in your relation. So it's the same as a cardinality, actually. Yeah? So that's, I'm not sure whether that's useful information. So basically, what's happening here is there's just one horizontal partition. Yeah, the input relation becomes that one horizontal partition. You don't partition anything. Yeah, and based on that horizontal partition, you create one output tuple. Yeah, so basically, if you have 3 tuples in the output, well, that is because there were 3 horizontal partitions in step 2. 2 horizontal partitions in step 2, and so forth. So that is grouping. Yeah? Then there's a lot of conditions and what you can do and stuff. Maybe we now go to the notebook a little bit. So here, that's this gender query. We use a different color again. I think it's the same as in the notebook. So it's really important that you get that to understand this grouper operator, because it will reappear 2 weeks from now, roughly, in another language called SQL that uses very similar ideas. And it's important you really understand those 3 steps. Here's another example where we specify more than one aggregation function. You can specify multiple attributes to group on, to partition on, yeah, to have an equality condition. That's okay, but that's basically. Sorry, I was on marked the wrong thing. So those are 2 attributes being specified for the equality condition, but you can also specify multiple aggregation functions here. And that is what's happening here. Yeah, so here I'm creating, so what exactly, how are the aggregates computed here again? Could someone explain to me? So how is that query along the 3 steps? What does it mean if you have 3 aggregation functions? It's 3, yeah. How do the steps look like for this specific query? The 3 steps I just explained. Here's this 3 steps again. Where the, yeah, those are the 3 steps here on the slides: grouping, aggregation, projection. But now we have, yeah, we have multiple aggregation functions. So what does it mean? How is this query computed along those steps? What's the grouping condition, or what is the property of those horizontal partitions? How many horizontal partitions do we have? How many horizontal partitions do we have? Yeah, with a yellow. 32, correct. Yeah, so it's skipping 22 out of 32 tuples, only showing 10. Yeah, so it's 32 tuples, so there must have been 32 horizontal partitions. That's correct. Yeah, and what is the condition? What's the invariant for each of those horizontal partitions? What holds? Which condition holds within each and every horizontal partition? Yeah. The year is equal. Yeah, for whatever tuple, whatever pair of tuples you look at inside a horizontal partition, the year attribute value is equal. It's the same. Yeah, so there's a horizontal partition where all of the attributes have a year 1995. There's one where all have a 96, and so forth and so forth. Yeah, you will see that our toy example is a bit stupid because, yeah. Yeah, it doesn't make too much sense, right? Yeah, so that's not the standard case. You will have more tuples, but so the IMDb toy data set we're using only has the movies of these 3 directors. Yeah, and that's the reason probably. Maybe if you show more of those, you will have better, bigger groups, hopefully. Yeah, and then there's a sum. So that's the sum of the IDs within each horizontal partition. Does it make sense to have that aggregation function? And if I ask like that, does it make sense? So the answer is with high likelihood, no. Again, ID is a symbol. Doing a sum over a symbol doesn't make any sense. Yeah? It's like sorting. Average, does it make sense on an ID attribute? No, definitely not. Doesn't make any sense. It's just to show you, yeah. I mean, for analytics, you would probably have more meaningful aggregations, like what is the sum of the revenue of those movies, or whatever the maximum number of people that went to a theater or something like that, if that information is available in your database. Okay. Oh, that's the stuff I wrote here. Yeah, and basically on the operator level, on the tree level, it looks as that. Yeah? So we use another color for that, and then all these conditions here. Okay. I think we had all of that. Yeah, so please play with that in the notebook. Make sure you understand this, split into these 3 steps. It's really important. We will see that over and over again. Yeah, so with that, let's do our final operator for today, and that's really the culmination of relational algebra, to my understanding, because it really illustrates the relationship of joins, theta joins, and grouping. And that's called co-grouping. That's an extension of relational algebra. It was proposed, I don't know, about 10 years ago. But if you understand this one, you really understand relational algebra. And what this means is, it's very similar to grouping, but it takes 2 inputs. You can also do it with 3 or 4, it doesn't matter, but for the moment let's do it with 2. So standard grouping operator only uses 1 input. It's unary, now this is binary. So I take 2 input relations, and maybe let's start with an example, makes it a bit easier. I take 2 input relations, but I group them together such that the output result of the operation contains these entries. What is this entry? This entry is basically an integer value Then there's a set with tuples from R and a set with tuples from S. And each of those big tuples, this is a tuple here, yeah? This is a tuple, contains the return of a partitioning function, the return value, which is 1. Yeah? So basically, here you need two partitioning functions that map to the same domain. That's what I'm trying to say with this definition here. Yeah? So you have two partitioning functions, one operating on R, one operating on S, but they share the same domain. That's very important. Here in this case, they both map to integer. So this PR partitioning function maps to int and returns the attribute value from the B attribute. And this PS partitioning function also maps to int and returns the value of the C attribute of S. Yeah? So this is returned B and S for the in both cases. And then this co-partitioning groups the tuples from the both inputs together. Yeah? So it's, okay, that was my return value of the partitioning function. And the tuples from R that had that return value for partitioning function PR are those tuples. Yeah? The tuples from S that had that return value were those tuples. Yeah, it's like the standard grouping or partitioning, however, now using those partitioning functions and grouping two input relations at the same time. Yeah, if you look at this, they had in their B value a 2, that's this 2, and they had in their C value a 2, that's these two. Yeah, so you have, it's always a return value, set, set. Yeah? And for each and every possible value you may have, you also see entries like this. Yeah, you will also see, this entry, for instance, so the return value was 6. Yeah, and that's this tuple from input relation R that has a return value 6 under partitioning function PR. However, from input relation S, there is no such tuple. Yeah, there is no tuple that from S that if you put it into PS returns 6. It doesn't exist. Yeah? Still, you build a partition like that. Yeah? That's called co-partitioning. And the interesting thing about that is you clearly see the relationship to joins. Again, I only show the example because now what you can do is, so this is the same result here as shown above. Yeah? This stuff is the same. Yeah? That's the result of the co-partitioning is this, not the stuff that's underneath. But now when you think about, okay, now assume I want to compute a join. Yeah? I don't want to do the co-partitioning. I don't want to have this stuff here. I have a join condition actually that could be the one as used above, and we had that in the example. Why do I write it? So above, and we had this join condition. Maybe I go back to that slide. When we defined the theta join, here we had this condition, this B equals C condition, this join predicate. Yeah? That is typically a condition along a foreign key, as mentioned before. And now we do something similar in this co-grouping as we say, so where's my example? Oh, come on, here's my example. I kind of implicitly have that join condition here because I say, okay, here I use partition on B, R is partitioned on B. Now S is partitioned on C. So what does that imply for computing the join? So what I'm trying to, so my question is, now I computed the co-partitioning, I did the co-grouping. How do I get to the join result, assuming that B equals C? If my join condition in the theta join is B equals C, and the input is the same here, the input is R, S. How do I get from this co-grouping, that's a rejoin, that's the result of the co-group operator, to the result of the theta join? Does anyone see that? Yeah. Yes, excellent. That's a cross product on what exactly? How do you use the cross product here? Is it one or many cross products? Yeah, you want to? Yeah, what is the first one and the second one?
First couple of the first category and the first couple of the second category. So for example,
Yeah, okay, right. So what you do is, to get to the join, is you simply do a cross product of this relation with that relation. Yeah, with this relation and that relation, this and that is empty, this and that is empty anyway. Yeah, so that's why you have 4 tuples here, because you already partitioned on that equi join condition. You brought tuple together where you know this attribute value B is 2 and the attribute value C is 2. That's exactly what this is representing in the join, in the result. So the only difference to get from here to the result of the theta join is to compute the cross product of those 2 sets, and that's exactly this. And here you see, hey, everything is correct. Yeah, and by doing that, you actually it's guaranteed that you get the right join result for an equi join. So this sounds a nice theoretical exercise, but actually this algorithm, doing the co-grouping and then doing the cross product, is used in many, many scenarios in real systems, be it a single system, but also for distributed cases. Assume you have data distributed across multiple servers. This is the join you're going to run later on. Yeah? But we have to think about how to do it algorithmically, but the core idea will always be something like that. Yeah? So that's really important to understand that. Okay, so with that, so what are the data management and analysis issues behind that? We had question 3, how do we query this data with relational algebra? And that's what we looked at today. So we did a transfer already using these examples, but just for the remaining 5 minutes or so, if you go back to what we had initially on the web page, yeah, when you phrase something like that, so many of the things you enter here can actually can be phrased as relational algebra expressions. Yeah, if you have a selection operator on movies, yeah, you can do something like that. Okay, this 5th element string should be contained in that name attribute of movies, and then you project it down to just show ID, name, and year. Yeah, that's okay. That you could do. Or you could also query the names of all actors of the selected films with this expression. That's okay. Yeah, you can do things like if you click on the web page on the 5th element in the web browser, yeah, you select the films with this ID from the list generated above, and then you can do a query like that. Yeah. So many things you do on the web page can be expressed with these relational algebra expressions. What's a bit harder is stuff like not all main actors, but only k-many actors, just returning a subset of the result set, yeah, including so orders, sorting, stuff like that. We didn't talk about that at all. So only the greatest, most important actors, for instance. So on IMDb, you see the cast is always displayed in the order of importance. Yeah? So the main actors are shown first, like Bruce Willis in that example, and so forth. Yeah? So that we can't really express with relational algebra. So looking ahead to next week, so unfortunately, these expressions are sometimes a bit hard to read. Yeah? Therefore, another option is to hide relational algebra expressions under another language. Yeah? Design another query language and then translate that to relational algebra. And that brings us back to the fundamental theorem of software engineering. We can solve any problem by introducing an extra level of indirection, except for the problem of too many levels of indirections. Yeah, that's basically what computer scientists are doing. Actually, what's happening right now, getting back to ChatGPT, we're adding another language on top. Natural language translating to relational algebra. Yeah, that's currently happening. It works pretty well in many cases. Yeah? Yeah, so I added some literature. So some of it is in German, videos from older lectures. Again, those are the chapters in the Kemper Eichler. The English option is Masrina Warte. And what I highly recommend is this website. That's a relational algebra calculator that already has the data we use in this lecture already loaded, and you can directly play with relational algebra expressions to get going and learn this stuff. Yeah, so good luck with that. See you next week.